Hello everyone. I'll be going over divergence theorem and we'll be verifying it using previous methods where we use like n hat, d sigma die with f with surface integrals, and then we'll do just and to prove that the divergence theorem, which is a volume integral, that they can both work. So this is just to tell you all, this will probably be everything I'm doing here will be one big problem. There'll be like one whole page on your exam. So I'm just going to go ahead and get started. So the first part is to project S1 and S2 into the y-x plane. So looking at it, this is S1. Sorry, you can't see it very well. This thing's in the way. S1 is part of a sphere. It is a sphere. Because if you rewrite it, you can get z squared plus x squared plus y squared equal to 2, which means it's rho squared equal to 2, which means rho is equal to square root of 2. So let's go write that out because I want to use this later anyways. And S1 is just a plane. It kind of cuts off, like it's the bottom part of this region, and it's what it looks like is essentially like if you cut off like the top of part of an orange. This is what it would look like. You could just this is kind of like a dome-like shape. So get right into it. To project the y-x plane. So since we know that this is a sphere, we want to look at where z1 or s2 and s1 intersect, which is this circle right here where z equals 1. So if z equals 1, we'll do the work down here, then that means that you have 1 equal to square root of 2 minus x squared minus y squared, which implies x squared plus y squared equals 1, which implies r equals to 1. So if r equals to 1, that means that this is definitely a circle with a radius of 1. Close enough. So r equals to 1. So this is what it looks like as a projection in the y-x plane. So now go on to the next part to do the surface integral. So like I did here at the top, I solved for the surface 1 in terms of to a constant. So I have to do the same thing here. This has to equal a constant, which would be 2. So which equals x squared plus y squared. Whoops. Plus z squared. So now I have to do n hat d sigma. And just to remind you all, n hat is del f. It's a unit vector. So it's going to be del f over the magnitude of del f. So it has it's just adding on direction to this d sigma, where d sigma is a magnitude, which correlates to del f and the area of our region. So, and I'm putting this cross here because I don't want to put a dot for multiplication because I don't want this to be a dot product. It's a vector times a magnitude. So, so the d sigma is the magnitude of del f over fz. In this case, the reason I chose fz because if looking at a projection, we don't see z as one of our axes, or you can be like, oh, we're looking down from our positive z axis as our perspective. So that's what our z is, because then our dA is going to be wherever our projection is, and we can't have whatever like axes that isn't part of our area with this. So since z is not in this the area that we're looking at, the z goes in the denominator for f of z. So then, this is the magnitude of del f, by the way. So then you can cross these two out. So you just have to do del f over magnitude of sz. So del f is going to be equal to, I'm just going to do all this at once. So it's going to be 2x I plus 2y j plus 2zk, all divided by fz. So typically fz is typically 1 or something, but in this case fz is going to be 2z. So make note of that, because I know usually it's 1 and it makes the math a little easier, but watch out for something like this. So it's going to be 2z in this case. And with our dA tagged for xy, typed at the end there. Now, I'm going to simplify this down further. So this becomes x over z I plus y over z j plus k dA xy. So now, in order to do the double integral, I have to do f dot n hat d sigma. So with f, so I want to go ahead and solve that up here, and then I'll plug it in. Or I'll go ahead and get it started. So n hat d sigma would equal, since f is equal to xi plus yj plus zk, only multiplying x to the I term, y to the j term, and z to the k term. So it's going to be x squared over z, and I'm adding up all these different terms up since it's a dot product, y squared over z plus z. They're dAxy. Alright, and this will equal double integral of x squared plus y squared. I'm going to put it all over the same denominator, since they both share it, plus z dAxy. So now it seems kind of it's an issue to how we find out the area. So in order to find out the area, we have to decide what terms are we going to do this in. Are we going to use rectangular with x and y, or are we going to use polar with r and theta? So looking at it, since it's a circle, you want to use polar coordinates. So we have to convert x, y, and z all into r's and thetas. And so so it's going to be, we have x squared plus y squared, so we can say this is r squared here. And z is equal to, going back up to here, to the original way that our surface 1 is written. We can say that z is equal to the square root of 2 minus r squared, since we can just replace negative x squared minus y squared with negative r squared. So we can plug in we can use this to plug in for everything, and for our dA xy, we'll say it would be equal to r d theta. So then this would equal the double integral of r squared over 2 minus r squared square root plus the square root of 2 minus r squared dA. Oh, sorry, r d theta. Go ahead and multiply that r out. And we're also solve for our limits. So we're going to have r cubed over square root of 2 minus r squared plus the square root of 2 minus r squared. Sorry, times r dr d theta. So to find the limits for our r, we just take we go from the center of our circle out. We hit r equal to 0 and exit r equal to 1. So go from 0 to 1. And for theta, look at the positive x-axis and go around a circle till we either hit the same spot or exit. And in this case, we'll go from 0 to 2 pi, which is a normal case. Now, issue is we can't exactly integrate this left term, r cubed over square root 2 minus r squared. There's an issue with it. So we need to find a way to make that more integratable. So issue being that our du would be just an r, but we have r cubed. So we need to find out how we can do this. So a good step you can try is to find a common denominator between your two terms and see what you get. And when you do that, you'll get r cubed plus, and when we multiply by the square root of 2 minus r squared to the top and the bottom of your right term, you would just get that same term. So it becomes r times 2 minus r squared, but all over the same denominator, square root of 2 minus r squared, dr d theta. And I can multiply this r throughout, so then this becomes plus 2r minus r cubed, which is great because we can get rid of this r cubed. Now our du matches up. We now have one singular r. So now we can integrate this. So I want to rewrite this to make it a little bit easier, or just my preference. I like having it as I give parentheses for radicals. I just realized I wrote two radicals right here. 2 minus r squared to the negative 1/2 dr d theta. So now we can integrate. So if we integrate, we can add 1 to the exponent to the parentheses portion. So that would be 2 minus r squared to the 1/2. And then I'm going to multiply by, or divide by 1/2. So it would be multiply by 2 and divide by our du. So if we have 2r divided by our du, which is negative 2r, we'll end up getting a negative in front. So I have negative 2 times this. And then we'll be evaluating this from 0 to 1 d theta. So then this would equal 0 to 2 pi of negative 2 times, so it's going to be 2 minus 1 squared, which is 1 to the 1/2, minus 2 minus 0 to the 1/2 d theta. So this would equal negative 2 from 0 to 2 pi of 1 minus the square root of 2 d theta. Integrating in terms of theta, it's going to be negative 2 times 1 minus square root of 2 times theta, where theta is going to go from 0 to 2 pi. So this would end up equaling 4 pi, negative 4 pi, or we'll say 4 pi. So let me, sorry, pin malfunction. I think my battery's starting to die. So I have 4 pi times square root of 2 minus 1. Alright, so I kind of just pull out a negative, so I have square root of 2 minus 1 and times that by 4 pi. So this is going to be our flux for our S1. So now I need to do it for S2. So for S2, it's z equal to 1. So we can, but yeah, let's say z equal to 1. So n hat d sigma, so it's going to be del f. Del f over fz, magnitude of fz dA. In this case, our del f is just b k. Fz would be 1. So then our dA, let's leave as x, y, dxy. And we dot this with our f, where f is xi plus yj plus zk. Since the n hat d sigma does not have an I or j term, it'll just be zk dotted with k dAxy, so it ends up equaling z dAxy. So you plug this in. So if it's z, and we're going to do the same method as before, we do it in terms of r and theta, we're going to have to make z equal to 1 for our surface. Area going to be, dA is going to end up being drd theta. Same limits as before, 0 to 1, 0 to 2 pi. So then this would equal r squared over 2, from 0 to 1, d theta. This would equal 0 to 2 pi, 1 half minus 0, so 1 half d theta, and then this would equal 1 half times theta from 0 to 2 pi, so we'll end up getting pi. Oh, my bad. I believe I made an error. So I was going to show you why what I did was wrong. So I assumed, so in this first part, I forgot to let you all know, but we have to look at our n hats for this. So for surface 1, n hat was positive, so we needed a positive x squared, y squared, and z squared, which we did have for our S1 here. So that was good. But, and so like when we go around, we went clockwise, which is good. But for S2, we have to look at n hat as in what direction it's going, and make a note of it. Since it's going downward, it actually is a negative z with a negative 1, although it doesn't change the surface at all. It does change the surface, but it does not change your like what you plug in. And the only difference would be that we'd had a negative k and a negative z, but when you plug in for that, you have a negative 1. So everything comes negative. So we'll have a negative, negative, negative. So then equals negative pi. So this is how you would, sorry, and if I lost you all, I'm very sorry about that. But I don't want to go back there and do all this work again. Just so I don't have this error in there. But the reason why it's negative is because we're going downward. And we have to account for that, but with our surface, which is as a negative z. So that's why we go from 0 to 2 pi. And you could have left it as z equal to 1, but made sure that you flipped your limits. So either way, you could have made this positive, but you have to account for it in your limits. Or you could just make a negative to begin with, and then your limits would still account for it. So this is something to keep in mind, especially when you have surfaces that are pointing downward. Z is usually a good indicator of what sign to make it. If you're looking at the Z, if you make an arrow going out and it's going downward, then you need to make sure that your Z is negative. If it's going upward, maybe make sure your Z is positive. So just one thing to look out for. If you're still confused, please comment or email me or anything. I don't mind answering any more questions. I'll address this at SI anyways. So then for the surface, for the total one, it's going to be double integral of S1 plus double integral of S2, which would be 4 pi square root of 2 minus 1 minus pi. So we can simplify this down to being 4 pi square root of 2 minus 5 pi. So this is all the surface integral part. But now we have to get the same answer for our volume integral part. So for our volume integral part, do triple integral of del dot f dv. So then this would equal delta f, where del is just the partial of x, like the partial with respect to x, I, plus the partial with respect to y, j, plus the partial with respect to zk. I can write it right here just to show you all. I don't want to put it down here because it limits my work. So it'd be equal to partial with respect to x, I, plus partial with respect to y, j, plus partial with respect to zk. This we die with our mi plus nj. Oops, I just drew n twice. Nj plus pk. In this case, it's x, y, and z. So then you do the partial of each of those, which is going to be 1 plus 1 plus 1. So you end up getting 3 dv. So now we have to figure out what to do for our dv. I'm going to show you all, just so no one gets confused on where I got this 3. So you partial x, so that would just be 1 plus 1 plus 1, which equals 3. So now we have to figure out what to do for our dv. So we could do spherical if you wanted to. I would not suggest it, but you could. I would suggest doing cylindrical. And the reason why I say that is because we can solve this pretty easily in terms of z, r, and theta. We have it's not hard to make it equal to, like, have things in terms of z, in terms of r, in terms of theta, and there's nothing to account for in theta. So it's I feel like it's just kind of like the arbitrary choice of picking which one, but I think it's easiest with cylindrical coordinates. So I'm going to go ahead and account for all that. So I'm going to go ahead and change this dv to being dz dr theta. So then for our z, we shoot our arrow upward. We hit z equal to 1, then exit z equal to, since this has to be in terms of r, square root of 2 minus r squared. So we go from 1 to square root of 2 minus r squared. And we can use the same limits for r and theta that we did for the first two. So because we're going to look at our r, we're going to go from our center outward, so 0 to 1. And then for our theta, we'll go from 0 to 2 pi. So now we're going to go ahead and integrate z. So it's going to be 3 times z from 1 to square root of 2 minus r squared, which I'm just going to go. So 1 square root 2 minus r squared, r d theta, which equals 0 to 2 pi, 0 to 1. I'm going to put this 3 to the outside because I don't have to deal with it. Then becomes 2 minus r squared minus 1. I'm going to have to multiply the r through. So it becomes r times square root of 2 minus r squared minus r dr d theta. So now we have we have a du for r square root of 2 minus r squared, and we can integrate r really easily. So go ahead and integrate this in all terms of r. So this will equal 0 to 2 pi of, and then I'm going to write this in parentheses, 2 minus r squared to the 3 halves. And then I'm going to divide by negative 2r. So it becomes, so the divide by 3 halves, so we're going to be multiplied by 2/3, and I'm going to divide by negative 2r from r, so we have times negative 1/2 minus r squared over 2. Just go from 0 to 1, d theta. So then this would equal I'm for my 3 on the outside. Actually, I'll go ahead and multiply my 3 in since it'll cancel out that 1/3. So that would equal negative 0 to 2 pi. So I'll pull out the negative. By the way, I just pull out all these coefficients, cancel out the 2, cancel out the 3's, and pull out the negative. Oh crap, I just realized I can't do that. That was bad math on my part. I forgot how this r squared over 2. So I was going to multiply the 3 throughout, so this is negative 1/3. So then I'll have a negative 2 minus r squared 3/2 minus r squared over 2, and this is times 3 since I multiply that 3 throughout. I'm still going from 0 to 1 times d theta, so this will equal 0 to 2 pi of, this is going to be negative 2 minus 1 to 3/2 minus 3/2 over 2 of 1 minus 0. D theta. And this will equal 0 to 2 pi. Well, what did I just do? And I am messing up right now. Very sorry. 2 minus 0 to 3/2 minus 3/2 of 1 minus 0. Might be distracted here. So then this will equal from 0 to 2 pi. This would be 1 to 3/2 minus 2 to 3/2. That would be negative. So we'll have a negative 1 plus 2 square root of 2 minus 3/2. D theta. So then this will go ahead, this will equal square root of 2 over 2. And this would be minus 5/2 times the integral of theta, like the integral for theta, which is just theta from 0 to 2 pi. And this will equal 2 pi times 2 square root of 2 minus 5/2. This would equal 4 pi square root of 2 minus 5 pi, which is exactly what we got at the top there. And then you can say, therefore, divergence theorem is verified. Sorry again for the little errors I made. I at least corrected them. Overall, things to look out for is your in-hat directions, because that's important in deciding the value, like the sign of whatever surface integral you're doing. And also memorize the equations for n hat d sigma, and knowing how to make your function equal a constant. I mean, it's really easy, but you know that's something that you need to know how to do in order to find out n hat d sigma. You have to look. When you have to do the volume part, you have to reach back into unit 4 and 5 on how to do volumes. So I'm sorry if those units did not go well for you. They didn't go well for me either. But hopefully the second time around when you try to do them, they make more sense and it's more doable to find a volume. And they're most likely you're going to have to do a verification problem anyways. So like this will be one page of your test if I haven't already said that. So definitely make sure that your answers are the same if they're not. Like I think literally on my test last year, I forgot to account for the negative sign on the second surface, and then when I solved for the volume part, and I got that I had negative 5 pi instead of I had negative 5 pi here, and I had negative 3 pi here. I realized I made a mistake. So, you can realize these mistakes pretty easily, especially if you can do the divergence theorem part with the volume integral. Because if you're able to do that well, then you're able to confirm all, because of the surface integral parts, which I think I make the most errors in, and most people make the most errors in, because there's just so many different steps you have to do. You can just make the very error, like an error on this very last part where you don't add them together right. But so make sure that you account for your signs, especially for your n hat and d sigma, and make sure that your answers are the same. I really hope this helps. Sorry again for the errors. I'm really tired. Happy 4th of July as well. Good luck on your tests on Thursday.